Hello, class. Welcome back to online chemistry. We are going to continue on with our stoichiometry work. Today, we're going to be dealing with moles and mole conversions. So Friday, if you did the assignment Friday, if not, you need to email me so I can open it back up. You're still going to be counted absent on Friday, but you don't want to get a zero along with that too. So if you did not finish with the assignment on Friday, just let me know and I can open it back up for you. But you will need to complete the assignment today in order to get counted for counted present for today. So please make sure you're keeping up with your assignments and trying to do each assignment every day so you don't get behind. So with that being said, we're going to talk about mole conversions today. If you did do the assignment Friday, or at least start to try it, you may have had some difficulty with some of the numbers and the math because we're dealing with really, really big numbers here. And in the video on Friday, I kind of showed you how large a mole is, how many things that is. And it's a really, really large number. 1 mole of a substance has the Avogadro's number of atoms in it. So 1 mole of anything will have 6.022 times 10 to the 23rd power of things in it. So if I have a mole of salt, I will have 6.022 times 10 to the 23rd molecules of salt in it. If I have a mole of pennies, I would have 6.022 times 10 to the 23rd pennies. That would also make me the richest person on the planet. I could probably buy the entire planet and still have extra money left over. This is a really, really large number. Just to show you, it is 602 billion trillion. Like if you were talking dollars and I had a mole of dollar bills, I would have 602 billion trillion dollars. It's also, so if I write it out, it's 6, 0, 2, 2, and then 20 zeros after that. Boom. And so this is Avogadro's number. Did I do that right? Oh, that goes over here. This is a mole of something. 602 sextillion or 602 billion trillion. And so it is a really, really large number. And anytime I have a mole of something, whether it's a mole of a chemical or a mole of anything else, this is the number of those things that I have, whether it's atoms or electrons or whatever you're trying to count. If I have a mole of that thing, this is how many I have. In the same way, if I have a dozen of anything, I have 12 of those things. If I have a dozen pennies, I have 12 cents. If I have a dozen roses, I have 12 roses. If I have a dozen donuts, I have 12 donuts. If I have a mole of donuts, this is how many donuts I have. The entire world would be covered with donuts. If I have a mole of roses, this is how many roses I would have. The entire world would be covered with roses. And so this is a very, very large number. Now, today, we're going to get into conversions. And I'm going to go back to the PowerPoint. We're going to go through some of the things on the PowerPoint, and I will give you some examples on the board as to how we do these conversions. So, starting off, they talk about mole conversions being the building blocks for future stoichiometric calculations. I already talked to you about stoichiometry. And so as we do more and more math in stoichiometry, you're going to need to do more and more mole conversions. The good news is they kind of have a system for this. And once you learn to use the system, it becomes a lot easier. As you're learning to do it, it is kind of difficult. So we're going to start off with one of the easier ones because you don't have a lot of large numbers in this one. We're going to start off with mole to mass conversion. So if I'm converting from a number of moles to a number of grams, I need to go back and forth in between these. Sometimes they give you moles and they ask you how heavy it is. Sometimes they give you a certain amount of weight of a chemical and ask you how many moles you have. And so in order to go back and forth in between moles and grams, I need to use a thing called the molar mass. The molar mass is something we get from the periodic table. It is the atomic mass on the periodic table. So as I look at these elements on the periodic table, the number at the bottom is the number that I'm going to use for my molar mass or my atomic mass. So for gold, which is AU, the number there is going to be 196.96. And so that is my molar mass. That is my atomic mass. If I have 1 mole of gold, or 6.022 times 10 to the 23rd atoms of gold, how much does that weigh? It weighs 196.96 grams for every 1 mole that I weigh. And so we're going to use these numbers on the periodic table to convert back and forth into and out of moles. Now, something I want to remind you of that we've kind of seen before we get into these steps is using conversion factors. And the idea behind conversion factors is converting from one unit to another. And the whole idea is I make a fraction that's equal on top and bottom. So if I have 1 over 1, that is equal to 1. Anything top and bottom is the same on my fractions, that's going to be equal to 1. So if I have 4 over 4, that is also equal to 1. Let me turn the lights back off because I think maybe you can see it better. There's a lot of glare on the board. So 4 over 4 is also equal to 1. If I have 400 over 400, the top and bottom are equal, it's equal to 1. Now, if I change this a little bit and I use 2 different units, like if I have $1 bill or 4 25-cent pieces or quarters, is $1 equal to 4 quarters? Yes, it is. So the top and bottom are still equal amounts. So the fraction is still equal to 1. And so this is what I'm looking to set up. I want my top and my bottom to be the same amount, just different units. One of them might be weight. The other one might be number of molecules or number of moles. But if I can make a conversion between those, I can use this to do a little bit of math. So for instance, if I use the dollars and quarters one, like I have $1 on top and 4 quarters on bottom, let's say I have, let's just pick a random number, 792 quarters. And I want to know how much money that is in regular dollars, because who carries around 792 quarters? I need to know how much money I have. And so I'm going to use this conversion factor to do that. In order to set this up, I'm just going to multiply by my conversion factor, $1 over 4 25-cent pieces or quarters. And if this helps you to kind of memorize this, you can put this over 1, because if I divide by 1, nothing really matters here. It's not changing anything. So the math that I'm going to do here is I'm going to take my number, 792 quarters, times 1, and then divide by 4. If it's on top, you multiply. If it's on bottom, you divide. And so how many dollars is in that 792 quarters? Well, on my calculator, I take 792 and I divide by 4. And the answer is exactly, I didn't know it was going to be this, but it's exactly $198. I just divided by 4 to get there. 792 divided by 4. I would have gotten the same thing if I multiplied by 1, but multiplying by 1 is not going to change anything. So I could have done 792 times 1 and then divide by 4, and I still would have gotten 198. And so this is how we're going to kind of set up these problems and see if we can get to a number of moles that makes sense. Now, for the mole ratio, not mole ratio, we'll get to mole ratio later. For our molar mass conversion, we're going to use the number off of the periodic table. And all of these numbers at the bottom here, the bottom number in the block for your particular element is going to tell you how much it weighs in grams for 1 mole. So 1 mole equals that many grams for that particular element if you use the bottom number. So We have 3 steps here. Step 1, write the given value with the units. So we got to get the number that they give us and write it down with the units. We need to know about the units. You have to keep track of your units. Step 2, use the molar mass, which we get from the periodic table. Use the molar mass of the substance as a conversion factor, like I just made on the board over there, making sure to set up the conversion so that the given units cancel out and the desired units are left. I'll show you that in just a second. And then step 3, execute the calculation. That basically just means do the math. So do the math that's left over and get your answer. So their example question is, what is the mass of 3.01 moles of iron Fe? So we got a couple steps to do here. Step 1, I need to write down what they give me. I need to take the units that they give me and write them down so I know what I'm dealing with here. So I have 3.01 moles of iron, Fe. And just for my own visual purposes, I'm going to put this over 1. If I divide by 1, it doesn't change anything. It just keeps it like it is. It's just going to show me what's on top and what's on bottom so I know what to do next. So here, I need to make a conversion factor. Now, how much does iron weigh if I have 1 mole? So I'm going to find it on the periodic table. Iron is right there, Fe, on the periodic table. And you look it up on your periodic table. You can find one online. You can probably have a link to one on Sapling. And so you look at the number at the bottom. That's your atomic mass. It's also your molar mass. It will tell you how much 1 mole of iron weighs. And so here on my periodic table, iron, all right, so over here, everybody can see it. Iron is equal to 55.845 grams per mole. So for every 1 mole, it's 55.845 grams. So when I make my conversion factor here, the key is I want moles to cancel out. I want moles to go away, and I want to be left in grams over here. And so when I set up this conversion factor, I'm going to have grams on top and moles on bottom. Because if I combine these fractions, the moles is going to be on top and bottom. And anything over itself as a fraction, like if I write this over here, moles over moles, just units, no numbers. Moles over moles as a fraction is equal to what? It's equal to 1. And is multiplying or dividing by 1 going to change my problem at all? No, it's not. Anything multiplied by itself or divided by itself is still just itself. So this can actually get canceled out and go away. And that's what I want to happen. I want the moles to go away. And so I want to set it up where I have moles on top and moles on bottom, and that's going to allow me to cancel those out. So if my moles are on bottom, my grams need to be on top. That's what I want to finish in. That's the last step that I need. And so now I'm going to take these numbers and I'm going to make my conversion factor out of this. So 1 mole is equal to 55.845 grams. And I got this off the periodic table. 55.845 grams. And that's moles of iron and grams of iron. So now that's my problem. It's set up like it should be. What do I do if I always start with this number. This is going to be the first number I put in my calculator. You're going to move from left to right, just like you read. So I start with this number in my calculator. And when I go to the next fraction, if a number's on top, I multiply. If a number's on bottom, I divide. And so the math that I need to do here is 3.01 times 55.845 divide by 1. You can skip the divide by 1 at the end if you want to, because it's not going to change your answer. But if you do it, it's also not going to hurt you, whichever way you feel most comfortable doing. So I'm going to put that in my calculator, 3.01 times 55.845. And my answer that I get out is 168.09345. 168.09 grams of iron. And so that's how many grams of iron, 168.09, are in 3.01 moles of iron. It's not a very long problem. The only thing I really had to figure out was what is the conversion factor. and set it up. And I got that directly from the periodic table. So it's not difficult to find. It's right here. Everybody has a periodic table. So this is their example problem. Let's go back to the board and see that they did it the exact same way that I did it. What's the given mass that they gave me? They gave me 3.01 moles of iron. That's my given value with units. What is the molar mass for iron? I get it right off the periodic table. It's 55.845. And so I set up my conversion factor with 55.847 grams of iron. Theirs is a little different than our periodic table. That's okay. 55.847 grams of iron over 1 mole, because that's equal to 1 mole of iron. And that's the math I'm going to do. You multiply the top numbers, divide by 1 if you want to, and you get your answer, which is 168 grams of iron, which is exactly what I got. So now, the next step, that one's the easy one with your molar mass. Now we're going to use Avogadro's number. We introduced Avogadro's number yesterday. That's the 6.022 times 10 to the 23rd power. This is a number we can use to get from moles over to particles. So if I tell you I have 1 mole of something, how many atoms do I have inside that mole? Well, I have Avogadro's number of atoms, 6.02 times 10 to the 23rd power, that really, really big long number. If I have 1 mole of anything, that's how many particles I have in that mole. Now, if I have multiple moles, I have to multiply by that number to get that number of particles. So you can kind of go back and forth multiplying or dividing, but you're going to set up a conversion factor just like we did. So their example here. Step 1, write the given value with units. You always have to figure out what they give you, what units they're in. Step 2, use Avogadro's number, the 6.022 times 10 to the 23rd power, as a conversion factor, making sure to set up the conversion so that given units cancel out and the desired units are left. Step 3, once you have everything set up, just do the math. Plug it all into your calculator and see what you get out. So let's do an example of that. How many moles are equivalent? So how many moles are equivalent? What does equivalent mean? It means equal. How many moles are equal to 2.41 times 10 to the 24th atoms of aluminum? So this time I'm going from atoms or particles to moles. They want to know how many moles are left over. So I'm going to come over here and set up my conversion factor and do the math on that. So let me come back to my board. And we're going to erase the last problem. We're going to start over with a new one. But it's going to be the same concept. I want to create a conversion factor. I want to cancel the things I want to get rid of out. And I want to get into my new setup. So the number they gave me was 2.41 times 10 to the 24th. 2.41 times 10 to the 24th power. And this is atoms of aluminum, Al. Atoms of aluminum. This is the number they gave me to start off with. This is where I need to begin my equation. Now, I'm just going to rewrite this over here to the side so I kind of restart. 2.41 times 10 to the 24th atoms of aluminum. I'm going to divide by 1. That's just for me. You don't have to do this if you don't want to, but I divide by 1 just to show me what's on top and what's on bottom. And now I need to bring in Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd. And this is how many atoms or particles are in 1 mole. So a mole is that many number of things in Avogadro's number. So if I have 1 mole of roses, like I said before, if I have 1 mole of roses, I have this many roses. So 1 mole is equal to Avogadro's number if you're counting however many things you have in that 1 mole. So here I have atoms and I need to get to moles. If I have atoms on top, I want to put atoms on bottom to get rid of that calculation so I can be only in moles. So when I set up my conversion factor here, I'm going to have the atoms on the bottom and I'm going to have moles on top. So I'm going to put mole on top and atoms on bottom. So next to the atoms, I put 6.022 times 10 to the 23rd. Next to the mole, I put 1. So I have 1 mole of aluminum and 6.022 times 10 to the 23rd atoms. So this is now my problem. It looks like a lot of numbers, but it's actually not that many numbers at all. What I've done is I've canceled out atoms on top and atoms on bottom, get to cancel out. And the only unit I have left is moles of aluminum. So atoms of aluminum and moles, or atoms of aluminum on top and atoms of aluminum on bottom cancel out. Now the math that I have to do, I take my 2.41 times 10 to the 24th power and divide by 6.022 times 10 to the 23rd power. Because it's on bottom. I can multiply by 1 if I want to. It's not going to change my answer. But if you want to multiply by the top, divide by the bottom, that's what you need to do. So I start with my number on the left. I go from left to right like always. And in my calculator, if you're using a calculator at home, it might be a little bit different, but I'm going to use brackets. So I open bracket, 2.41 times 10 to the 24th power, close bracket. And then I'm going to divide by this number on bottom. Because it's on bottom, I need to divide by it. Divide by, open a new bracket, 6.022 times 10 to the 23rd power, close the bracket, hit enter, and the answer I got is a wonderfully reasonable 4.00. 4.00 moles of aluminum. So that makes sense. If your answer is in moles, you want a really, really small number, usually in between 1 and 10, sometimes a little bit bigger, but you usually don't have hundreds of moles or thousands of moles, and you definitely don't have, something times 10 to the 24th or times 10 to the 23rd. That's just for how many atoms you have. Atoms is usually a very large number because you have a lot of them. If I have moles, it should be a reasonable number like that. And so if we come back here, we will see that they got to the exact same answer. They took the 2.41 times 10 to the 24th. That's the number of atoms they gave us to start off with. And then they want to convert to moles. So they set up the equation just like we had it set up over there. You're going to divide by Avogadro's number with atoms, because if atoms are on top and atoms are on bottom, they will cancel out. And the only unit you have left is moles on top. So Avogadro's number is 6.022 times 10 to the 23rd, and then 1 mole is how you're equal there. So 1 mole on top, Avogadro's number on bottom. Execute the calculation. Divide by Avogadro's number. Start with your number. Divide by Avogadro's number, and your answer should be 4.00 moles, which is exactly what I got. So they're going to have one more. So now we have a 2-step problem. They want to go big here. They're going to go from particles. They're going to go from particles all the way to grams or back and forth. So I need to use Avogadro's number, and I need to use the molar mass for that particular chemical. So same 3 setups, essentially. Step 1, figure out what they give you. What's the given value and the units for that? Step 2, use Avogadro's number and the molar mass this time to set up your conversion factors and make sure everything cancels out so you only have the units you want at the end. Step 3, execute the calculation. Do your actual math work in your calculator. So their example here, what is the mass? So they want to know, what is the mass? That's the thing they're asking me for. They want weight. It's probably going to be in grams. What is the mass in grams of 7.00 times 10 to the 33rd power of molecules? So what am I counting at the very beginning? I'm counting molecules. They're telling me how many molecules are in a certain amount of water. And at the end, I'm going to know how much that water weighs. So I need to use 2 things. I need to use Avogadro's number, and then I need to use the molar mass for H2O, for the formula H2O. I'm going to have to add up 2 hydrogens and 1 oxygen. So let's go over to the board and do this problem, and then we'll see if we got it right on sapling. So one last time, let me erase the previous problem. and I'm going to set this up. The number they gave me is 7.00 times 10 to the 33rd power. And I'm just going to do this all in one problem this time so I don't run out of room. 7.00 times 10 to the 33rd power, and this is molecules of H2O. I'm going to put this over 1 so I know that it's on top, and it helps me figure out what's on top and what's on bottom, whether I'm dividing and multiplying. Now, first thing I want to do is get rid of molecules. So in this conversion factor, if I have molecules on top and I want to cancel it out, the very next thing I need to do is put molecules on bottom. And it's got to be of H2O. That's what I'm keeping throughout all this. It's all going to be water. So molecules of H2O on top, molecules of H2O on bottom. Now, what is the number I use to count molecules? It's Avogadro's number. So we already saw before, Avogadro's number is 6.022 times 10 to the 23rd power, and that is equal to 1 mole. That's Avogadro's number. So if I'm making a conversion factor with molecules on the bottom, I need moles of H2O on top. And I'm going to use Avogadro's number and the number 1 for 1 mole here in my conversion factor. So I have 1 mole and 6.022 times 10 to the 23rd molecules of H2O. So that's my first conversion factor. Now I need to set up my second. What's the thing they want from me at the end here? They want to know, what is my mass? So I need to get the number of grams, how much my water actually weighs. Where do I get that number? From the periodic table. And so you'll remember the bottom number here for hydrogen and for oxygen is going to tell me how much grams 1 mole of those molecules weighs. So I actually have to do a little bit of math before I can set up this last one. I need H2O. So I need 1 oxygen and 2 hydrogens here. 1 oxygen and 2 hydrogens. So the oxygen, if I look on the periodic table, weighs 15.999. 15.999. And each hydrogen weighs 1.008. I have 2 of them. So I'm just going to add this 1.008, 1.008. And I add these together. 15.999, 1.008, 1.008. Add these together, and I get, I'm going to be honest, I don't want to do the math on this. No, let me do it. Don't be lazy. 8 plus 8 is 16. So I'm going to have 15.0, and that's going to be 18. 18.015, I believe. If I got it wrong, feel free to let me know. I'm not ashamed. Yes, I believe this is 18.015. Yeah, I think I'm good there. So that is how many grams of water you have in 1 mole. So if I have 1 mole of water, it weighs that many grams. Now, I don't know how many moles of water I'm going to have. I could go ahead and do this and know how many moles of water I have. We're going to do it all together. So the last step here, I have moles on top of H2O. I want to get rid of moles of H2O, and I want to get into water. So this right here is my next conversion factor. If I have 1 mole of H2O, and I put it on bottom this time, so top and bottom moles are going to cancel out. What is 1 mole of water equal to? 18.015 grams. 18.015 grams of H2O. And so now I have my problem set up. The only thing I need to do is the math, which is pretty easy. I just put it in the calculator. Well, it's not easy, but putting stuff in the calculator is easy. So I start with my first number, 7.00, open bracket, 7.00 times 10 to the 33rd power, close bracket. My next step, I can multiply by 1 if I want to, or I can just skip it because multiplying or dividing by 1 won't change anything. I'm going to divide, because this is on bottom, divide by Avogadro's number. So I hit divide, open bracket, 6.022 times 10 to the 23rd power, close bracket. And I'm just going to go ahead and hit enter here so I can write this down. And at this point, the answer I have is 1.1624 times 10 to the 10th power, which is actually quite a bit. 10 to the 10th power moles of water. This is not your answer, and most of the time you won't even stop here, but I just wanted to have a little reset. This is how many moles of water I have. And if each of these moles weighs 18.015 grams, I'm probably going to have a lot of grams too, because I need to multiply these together. So when I come in here and I multiply by the next number, which is going to be 18.015, I hit times 18.015. And my answer is, like I said, a little bit bigger than this. It's going to be 2.094. 2.094 times 10 to the 11th power grams of H2O. And just so you know, that's a pretty big number. If we write this out, it's going to be 2.094 and then eight more zeros. And that would be 209 billion grams. So how much does 7.00 times 10 to the 33 molecules of water weigh? How much does that weigh? It weighs 209 billion 400 million grams. That's the weight that you have. So this is going to be my final answer, 2.094 times 10 to the 11th power. That's grams of water, H2O. Let's make sure I got this right, because it's complicated math. It's not super easy, you know. So let's take a look. We start off with our 7.00 times 10 to the 33. We set up our conversion factors. They have the exact same conversion factors that I had. They start with their starting number. They're dividing by Avogadro's number and then multiplying by the molar mass for water, H2O, which they had to add up. 1 oxygen, 2 hydrogens. That's what water is. So they add that up and get the 18.015. Then your math is just going to be this number divided by that number times 18.015. And when you hit enter, you should get your answer, which was 2.09 times 10 to the 11th power, which is exactly what I got in grams of hydrogen. That's a lot of water. That's not a small amount of water. That's quite a bit of water. So that is the last problem I think that they have us doing today. I'm going to go ahead and stop the video here because it's already been a long video. So I hope that helps you out a little bit. I'm also going to make a second video that goes through just a couple of the problems on sapling. So that is available for you too, so you can actually see some of the problems on sapling as we do them. Because I know this is going to be a little difficult, especially trying to learn this from home. So please make sure that you're watching the videos and attempting to get done with the assignments. I'm still here in the empty classroom. Maybe you can see your seat from here. I know you miss it, but just try to be safe and do all the things that you're supposed to do at home, and hopefully we'll be able to come back soon. So thank you for watching today. Good luck on the assignment, and as always, if you have any questions, please email me. Thank you.